Right, so for those that don't know me, I'm a software engineer at ARM. I've been working for ARM for about 8 years, but joined the Fortran compiler team about a year ago. And during that time, I've been working on LLVM Flang, which I'll talk more about in a second. So if we next slide. Yeah, next slide. So Fortran is a long-established language in computing, and it's primarily used for maths and scientific calculations or scientific applications. It has lots of maths and floating point functionality that is useful for those who do that sort of thing. The complex type is part of the language. It's got good support for various array operations, like you can call sum and get the sum of all of your multi-dimensional array content in one single line. There's really little aliasing in standard Fortran, so you can do more aggressive optimizations than C and C++. It has built-in support for OpenMP and OpenACC, and it'll be 70 years old as a language in a couple of years. It's very popular in supercomputing, and there's a large code base of existing code that nobody really wants to rewrite that. Next slide. So LLVM Flang is a Fortran compiler on top of LLVM. It's written in C++, as is most of LLVM projects. It uses a multi-level, multi-level IR. I had it as mid-level IR in my head. It's a higher level of LLVM-IR in a sense, and there's a FIR dialect which models the Fortran constructs. That should allow us to do high-level optimization passes that are Fortran specific. We don't have much of that at the moment, but it'll come. We're currently merging the F18 LLVM project into LLVM main, and we should have Fortran 95 and OpenMP 1.1. And so far, the focus has been on making it feature complete rather than optimization. I will talk about optimization in a bit, and I want to point out that this is not a look how bad our compiler is. It's an attempt to find where we should start looking at optimizations specifically for Flang. Next slide. So I've been working with Snap, which is a small application to model a larger application that is used in some particle transport type stuff. I don't know what it actually does. It does a bunch of maths, but yeah, I don't understand it. It's not really important for me to understand what the application does, but it's a useful starting point for trying out the compiler on a real application. It's 8,500 lines of code. It uses OpenMP. It's Fortran 95. It's big enough to be interesting, but not so huge that it's impossible to manage. Next slide. So basically building and making it run took roughly 4 months. I'll try to cover that in 2 slides to not take all day. Next slide. So when we first started to build Snap, it's shown that there were some missing functionality in the compiler. So you got the linker errors when you try to link it. There's some built-in functions that weren't there. There were some bugs that appeared when we tried to run it, and some that appeared when we tried to compile it, like some OpenMP, OMP set nested. When you call that function, the compiler would crash. Some OpenMP unstructured constructs in Fortran failed to compile. And when using OpenMP, the induction variables in a parallel do loop would not be in memory and then passed as references, and then the callee would try to dereference the value 1 or something like that and crash. At first, we ran it with OpenMP turned off. Even that didn't work. See the bugs about sliced arrays, which didn't copy back. If you don't modify the actual variable you passed into a function, bad things happen. Once the basics were working, I turned on OpenMP, and yeah, there was lots of little bits and pieces that need fixing up. Some of which I did, some of which was other people helping me. And we now have something that works. You can take the F18 repository and compile compile Snap with the Flang compiler that comes with that. Next slide. So, like everyone who works on compilers, we want to know how fast or slow the code is. And given that we don't have any optimization enabled at all, you'd expect it to be fairly slow. And here's some relative performance numbers between GFortran and Flang. The orange ones are Flang, blue ones are GFortran. So about 6 times slower. With no optimization, you kind of expect that. This is GFortran with -03, so it's pretty aggressive. Next slide. So this is my main point of this presentation. Basically, what's the low-hanging fruit that we can pick up and work on? Next slide. So I measured the total execution time of Snap. That may not be the best way to measure this, but it's an easy one. And to make sure that it's not some specific to one processor or another, I picked 2 that are easy access when you work at ARM. We're not comparing x86 with ARM. I want to point out that they are not comparable processors. I just picked some that I had available to me, and they're not the same class processor. I also don't know how well GFortran or Flang, GFortran and LLVM compare on the 2 platforms, but that's beside the point. I made some modifications to make the test run for a little bit longer. That's just so that you get a representable measurement without too many errors from little tiny glitches. We ran with OpenMP enabled, but only 1 thread. And I was mostly using the perf tool to measure measure performance. And the measurements are relative to GFortran, where GFortran is 1.0. Next slide. So the first step, of course, is to try the various LLVM tools that are available. Flang itself doesn't optimize, but we can generate MLIR and or LLVM-IR and use the various tools that are available. I'm not going to go through the details here, but basically the result was that you don't get a huge amount of performance. I should point out that TCO that is mentioned here is a tool that is part of the original Flang implementation. You can do most of what TCO does with the Flang new these days. The summary is that there was no real benefit of running these tools. They did not improve the performance much. So next slide. So if the tools in LLVM itself can't help us much, we need to look at what we should be doing to make the code better for the LLVM tools, because I'm convinced they can do it. So I was using the MLIR output, which is the mid-level, multi-level IR, and modifying that by hand to just see, well, if the compiler were able to do what I wanted, what would the effect be? Next slide. So if we just compile with Flang and GFortran, the profiling or perf output looks a bit like this. What's noticeable is that the second function in the GFortran output is actually the first function in Flang, so it takes more than half the total time. Next slide. If we look at the code, it's 124 lines of Fortran code that contains one OpenMP parallel region, which has 11 nested loops. In those 11 nested loops, we have 10 places where we index into a 6-dimensional array called QIM. Each of those address calculations makes 59 MLIR or FIR operations and roughly 100 assembly instructions.
Yeah, we can share your screen. You're sharing your screen.
We seem to have lost the presentation. Okay. I think we moved the slide forward, but we get 100 assembly instructions just from that 6-dimensional array index, and it's repeated every time we index into the array. I looked at the innermost loop, which has another few indexes into complicated arrays. If you used to see, this looks like function calls, but they are actually index into arrays. And even if I use Clang -03 on the LLVM-IR generated by Flang, it doesn't optimize this much. The 2 lines inside that do loop makes 230 FIR operations in total. probably about 600 assembly instructions, give or take. Next slide. So if I move the address calculation out of the innermost loop and for all the 6 different array indices or index calculations in that little 2-line section, we get a 24% improvement in the total execution time. We're now only using 27% rather than 54% of the time in that function. So we'll move on to the next step. Next slide. So the next function I attacked is called dim3 sweep, or a module called dim3 sweep. And I found that it calls a standard Fortran function called sum, which in itself calls 3 different functions. And that leads to a lot of overhead because the arguments to the function is like 12 elements long. And writing my own function, sum1d and sum2d, for the common cases of calls to sum made the code run about 33% faster. Next slide. I then moved the malloc and free out of that loop as well, and that gives us a decent improvement. I also find that now sum1d gets inlined, which helps a bunch. So that's, yeah, just making things better. Move to the next slide. So if we take the hand optimized code that I moved the array indices out of index calculations out of the loop and compile it with Flang -03, it improves a bit more, about 12%. And next slide. So here's basically the all the optimizations that I did. From bottom is the slow original version, and the top is GFortran, but below that is the most optimized version that I did in this experiment. Next slide. So it's clear that some simple changes in the output of the compiler can make big improvements. We should make this happen inside the compiler rather than being something you do by hand. The lack of hoisting is due to missing alias information. I did a quick hack and it didn't work fully, but by compiling selected bits of snap with the alias set to always no alias, it improves the performance by a factor of 2. The calls to the sum function, we should have some sort of lib simplify the type path. And likewise, there is a path that translates alloc A into malloc and free for reducing stack usage. We should have a reverse one for small ones, and we probably should be able to hoist them out of loops as well. I have raised some GitHub tickets for solving these things. We do have a snap continuous integration test, so we don't break Flang when someone makes changes, basically. And there's a PR to snap to add Flang support. And we need to make Flang new, compile MLIR, then we could make it more simply for working on these things. And we need to add optimization to Flang new, or LLVM Flang. Next slide. So I want to say thanks to many people. I won't list them all, but there's people in ARM, there's people in NVIDIA or PGI that has helped. There's people in LANL and various other organizations that have contributed to the overall project, helped me personally. And yeah, without them, I wouldn't be doing this presentation. Questions, if we have time.
Yeah, I think we have time.
I have a question.
Yeah, go ahead.
May I? Yeah, so what is so special about this 6-dimensional array, QAM? Is it like allocatable array, or like is it using array descriptor?
Special in any real way. It's a 6-dimensional array. It's but it's heavily used in at least one of the big functions in the code. And there is a construct in Fortran that probably causes a bit of problems here. And that is that there's a descriptor for allocated memory and arrays in general. When you're passing them from one function to another, it's basically a data structure that is passed along, which contains the base pointer and the strides for the various dimensions, how many dimensions there are, and such things. And that, I think, is where the alias information for simple aliasing constructs is failing.
Okay, thank you. That makes sense.
I have a follow-up on that. So you had on your slide, you said aliasing hoisting is confirmed. But did you actually confirm it does the hoisting, or did you just see a reduction in end-to-end time?
So when I had the no alias, it does hoist the calculations of the addresses. I suspect what happens is that the standard alias calculations are simply saying, oh, this is too complicated, I don't know what's going on here, because there's a whole raft of read from something in a data structure, read something else from inside that same data structure, and read something else from that same data structure. And they're all the same data type as well. So if you use type-based information, they look like they're all potentially the same thing.
Right. I mean, well, there is aliasing concerns. There is other concerns with hoisting that. In when I looked at it, I didn't see the hoisting actually, but we can discuss that offline. There was a second question I was going to ask, but we have one in the chat first, so I'll wait.
Yeah.
Yeah. There's a question in chat, like, is there a build bot in place or coming soon that will add your snap CI and such like it to the build bot.
Okay, I'll take a look.